Okay, so liquid pressure, this is caused by, again, the impact of the particles on a surface, and it will increase with depth. So if you want to consider it in terms of layers of water, as you can see these slight gradations in the blue here, you've got the weight of the water at the top pressing down on the water here, and because this layer of water is not being pulled downwards, then this layer of water, the next layer of water, must be supporting it, and the only way it can support it is by having an upward pressure to support that weight of water. So all of the layers of water right at the bottom are supporting the layers of water further up, therefore the pressure must be higher to stop that water falling down. And we can see this when we look at a dam, for example. The pressure of the water, the force caused by that water, is much higher at the bottom, and therefore the wall to keep the dam back must be much thicker at the bottom and thinner at the top. Okay, so we can prove this quite simply by a container filled with water with holes at different heights, and when we let the water out, we see that the water at the bottom is transmitted sideways. It comes out much faster, and so it moves further across. So that's that line of water goes all the way there, whereas the one at the top, which is coming out at a lower pressure, so a lower speed, doesn't move as far across, and so it doesn't move as far across and ends up closer to the bottle. Okay, so liquid pressure increases with depth, so these two are proportional. Increases with depth. So they are proportional. And so floating and sinking in terms of weight and upthrust, including the use of force diagrams. We'll just carry on with pressure for a moment. Pressure acts in liquids equally in all directions. So pressure acts equally in all directions. So if you imagine a ball or a bag filled with water with holes in it, and you squeeze it, the water comes out in all directions at the same speed because of the water. The pressure within the water pushes out in all directions. And so this is one of these classic questions. What is the pressure at A and B and C and D and E? And if you look at these ones, you might predict that C, for example, or D, maybe E, has higher pressure than the ones with just a small volume of water above it. But of course, we're only really interested in the volume of water, or how deep the water is from this point to this point. So let's say that distance there is 5. The distance between C and the top of the water is also 5, and it's 5 there, and it's 5 there. And even though this one is sloping, so if we were to measure this distance here, it would be greater than 5 because this is on a slope. Actually, the distance between here and the top of the water is still exactly the same, 5. So the pressure at all of these points are the same. And we can see this when we look at this example here. You've got water higher at this point, which means the water pressure at this point must be higher than the water pressure here. So we've got a higher pressure and a lower pressure here, so small pressure, and therefore the pressure which is in that direction must be greater than the pressure in that direction. So when the tap opens, the water rushes through. So this water drops, this water goes up. That water drops down, that water drops up until the water is at the same height, and then you get the same pressure at this point and the same pressure at this point, and therefore there's no overall flow. So the heights of the water equalize. So we've decided in the previous couple of slides that liquid pressure increases with depth. So if we have an object in water, the pressure on the sides of the vessel from the water will be small at a small depth and then increase as you go further down. Now you'll have pressure on the bottom of the vessel or the object, and if it's got a large surface area, obviously you've got a large amount of pressure acting on it. If you have an object whereby its weight, so the weight is the arrow shown in orange here, and you have the upward pressure of the water, which is normally called upthrust or buoyancy. If the weight equals the upthrust, then the object will float. If the weight is greater than the upthrust, then the object sinks. Now, clearly, if this object is floating, then the upthrust, the upward water pressure, is equaling the weight. If this is a heavier object, then the object has to descend further in the water and so experience greater upthrust until it's balanced. And so we see this in ships when they don't have much cargo. They float very high in the water. So you get a ship and it's floating very high in the water if it hasn't got any cargo on it, and then as soon as it gets its cargo, it floats much lower in the water. Okay, so the base of the boat has to be further down in the water to reach the pressures whereby they can now counteract its greater weight. So this was parts of this were kind of realized very early on. Archimedes has a principle which basically says that if the weight of the water that is displaced equals the weight of the object displacing it, then the object will float. Okay, so if the weight of the object, or the weight of the object, will displace the same weight of the water, then the object floats. So obviously there'll be some objects which are very dense, so very dense metals or small volumes, whereby even when they're totally submerged, they can't displace enough water for them to float, and therefore they will always sink unless they get to very, very deep waters. But even then, some objects will just continue to sink down even though the pressure increases as it sinks, and will eventually hit the bottom of the water. Okay, so our force diagrams, if we were drawing this to show the forces, so if we just draw a simplified force diagram for this, for a floating object, and we want to label it. So there's our object, and it's floating in water. Then we can draw the weight arrow there, and we'll just put the upthrust arrow there, just for simplicity. Weight and upthrust. So normally when we're drawing the weight of an object, we would draw it at the center of the mass, down like that. And the upthrust, we would say acts at that point and comes up like that. So that would be a more correct way of doing it, but then you've got your force arrows overlapping, and so it's not quite as easy to interpret. And with force arrows, the strength of the force equals basically the length of the arrow. So if this is floating, then this arrow here should be the same length as this arrow here. Right, so that's weight up thrust and force diagrams. If we want to calculate pressure, and this is most easily done if we've got pressure in solids, then we're just doing the force applied divided by the area that force is applied over. The units here, so the units of force are the newtons. Area is normally measured in meters squared, so meter squared here. So the units of pressure are newtons per meter squared. So for every meter squared, how much force is applied. So the kind of question you might get is if 6 newtons was applied over 2 square meters, what is the pressure? So that would be a nice easy one. So that would just be pressure is 6 divided by 2 equals 3 meters squared. So a slightly more complex one was if 20 newtons was applied over a rectangular area of 2 by 4 meters, what would the pressure be? Okay, and so you'd still do pressure is force divided by area, so force is 20 newtons, and the area, because we've got a rectangle and we've got the sizes of it, you would just do the area there. So that would become 20 divided by 8, which equals 2.5. So 2.5 newtons per square meter. Oops, sorry, I got the units wrong up here. So always check your workings. Units per square meter. Nice example of this is stiletto heels. So these are very small heels, a very small area, and then trainers. So this is obviously one person. So you've got the same weight being applied. So that's the force on this sponge foam here, because the area is much larger. So here and here, that would be the same weight. This one, large area, and this one would be a small area. So if we look at our equation, force is directly proportional to pressure, whereas area is inversely proportional. So as the pressure goes up, as the area goes down, so because we've got a small area here, our area is going down, therefore our pressure is going up, and so therefore you get the object being pushed further into the foam than if you've got the larger area. So the classic example of this is if you pressed your thumb into a desk, you would feel that pressure on your thumb. If you press your thumb with the same force onto a needle or a pin, then you would feel a lot greater pain and your thumb would go through that needle. So that would be a nice example to think about.